right now? Yes, we have started the recording. Anyone? No? Okay. I am very interested to give you an explanation for this question, number 11. So it's one of my personally preferred question because this question does require some additional attention. So that's not it. Okay. Let's look at this question and try to break it down into parts. A girl of weight 550 Newton is playing on a seesaw with her brother. Figure 2.1 shows her brother of weight W is sitting 1.1 meter to the right of the balance point. The seesaw is balanced when the girl sits 0.86 meter to the left of the balance point. Calculate W. So here we have a balanced situation where we have two forces given on the figure and two perpendicular distances from the figure point is also given. So pretty straightforward. You have to, because the question says that the seesaw is currently in balance condition, you just go on for the principle of equilibrium of moment formula, F1 d1 equals to F2 d2. So in this case, this will be 550 into 0.86. If I just write 550 into 0.86, this should be equals to 1.1. Eliminate the moment first, force first, W into 1.1. So solve this for W, you get these 2 marks. Don't forget to write the units, it's important. Then the question says the girl and her brother slide equal distances along the seesaw away from each other. Describe and explain what happens. This is the interesting question that I'm very intrigued about. Have a look. Try to understand the statement of this thing. The girl and her brother slide equal distances along the seesaw away from each other. Try to understand what this means. The girl and her brother slide equal distances along the seesaw away from each other, which means both of these two people are gonna move towards their individual end of the seesaw and they're gonna move by equal distance. And then what's gonna happen? Describing excellence, what happens really means that will the equilibrium sustain or will the equilibrium get lost? Which side is gonna become bigger, which side is gonna become smaller? So let me just explain one simple thing for all of you to understand, that if we take a look at this ratio, what is the value of W? What is the value of W doing at here? W to value কত আসে দেখো তো?
It's 430.
430 Newton. Okay. So let's say I'm gonna just label these two distances. This is for the girl, this is for the boy. So if I just try to make a ratio of these two things, I'm using the variable because I want to show you something regarding the variable other than the exact constants. So in this case, 550 into this of the girl is equal to 430. Yes, 430 in distance of the boy. Now, the question says that both of them have moved at equal distances from this thing. And let's say both of them would go away by a small distance away from each other towards the end of the plank. So would this equilibrium remain same? Here's the deal. For this whole thing to be remaining equal, if I get a ratio of the girl distance divided by boy distance, this ratio is supposed to be 430 divided by 550. Now it says that both of them has increased by the same amount. What I want you to understand, what I want you to understand, that if I now add, so this is the ratio. So if I take a smaller version of this, so this is 43 by 55, which means the distances of these two parts should exist in this ratio, and only in that case can we have the two persons in equilibrium. Now, what I want you to appreciate that if I now add a number 43 by 55, let's say, of equal value, let's say 2, on both numerator and denominator side, would you end up with the same ratio or a different ratio?
Different ratio. Different ratio.
It will be a different ratio. Yeah, Samira, go ahead.
Why will it be 430 by 550? Shouldn't it be 550 by 430?
Because I have kept the girl distance on the left, on the top. So I'm taking this one on this side and this one on the bottom. I'm getting,
Okay, sir.
yeah, so, okay. So I'm making the ratio of the girl versus the boy. So yeah. So if we now add an equal value, equal number, and this number 2, this value of 2 is something that I just randomly picked. This is not from the question. This is just any random value. So if we just add equal number on the same side, on the numerator and the denominator side of this fraction, we're gonna get a different value. For example, in this case, we're gonna get 45 by 57. And one thing that I can tell you about the way proper fraction works, consider any proper fraction. Let's say if I go ahead and consider the very most simple of the proper fraction, let's say 1 by 2. If you start to add same number on both sides of the proper fraction, the total value of the proper fraction will slowly increase. So let's say if I add 1 on both sides, I'm going to get 2 by 3. This is 0.5, this is 0.67. If you add more, you're going to get 3 by 4. I'm just adding 1 on both sides. This is 0.75. If you add another one, you get 4 by 5. This is 0.80. If you add another one, you're going to get 5 by 6. This is nearly 0.9090, something like that. And it goes on, which means as long as we keep on adding the same number in the numerator and the denominator side, the ratio value slowly increases, but it will never become 1. Because this proper fraction will always be a proper fraction. For example, in this case, the difference between these two numbers, original numbers 43 and 55, we have a difference of about 7 plus 5, 12. We have a difference of about 12. So if we add equal numbers over here, even so, there will always be this difference of 12 between the denominator and the numerator. It goes without saying, which means this will always be a proper fraction, but it will be a different value, which means that in this case, our equilibrium will not sustain. Now comes the question that in which side will this fall down? In which side will this fall down? So I just wanted to show you the idea of fraction to give you a mathematical idea that this will not be the same, that this ratio of the girl distance versus boy distance will not remain exactly same if we start adding equal numbers on both sides. This is just a representation that I want you to have. You don't essentially have to use this equation to go ahead and explain this equation. I mean, explanation exact bhashata ekটু পরে বলতেছি, but do you understand the mathematical approach to understand this part, that if we add equal number to both the numerator and the denominator, we are not going to end up with the same exact ratio? Does this part make sense?
Yes.
ঠিক আছে? আচ্ছা, to make the whole thing work a bit better, let's say I'm going to work with this equation right now. This was our equilibrium equation. So let's try this. And just because we can, I'm not going to use variables over here. I'm going to use that exit values. So here we had 550 into 0.86, which was equal to 430 into 1.1. Okay. So the next part is actually really simple. Choose any value and add it with this distance for both of them and find out which one becomes larger. So let's say I'm going to increase both of them by 0.1. I'm just choosing a random number, 0.1. So if you choose a random number 0.1, so let's say in this case, this would become 550 into what, 0.86 plus 0.1. You could give any number here because the question says equal distance, so it doesn't say how much, so you could never give any number. It could as well be 1. So it could as well be 100. I really don't care. But I'm just giving 0.1 just to see what happens over here. And if I increase this by 0.1 as well, this will be, I'm going to give this sign. This is a made up sign. I have never seen this. But it just this just go ahead and mean that it's going to be equals to question mark. So we're trying to find it out. 430 into 1.1 plus 0.1. So how much are we going to get here? 515 to 0.87. I'm going to calculate rapidly. 478.5, and over here we're gonna get 430 into 1.2. We're getting 516. So you can see that by increasing the distance by equal amount, both of them are not having the exact same value of increment of the moment. Which one is having a bigger increase? Which moment is getting bigger?
The girls.
Hmm?
The girls moment. And the sisters.
How? Whenever both of them has moved away from each other by the same value of 0.1 meter, let's say, then the total moment, anti-clockwise moment of the girl is becoming 478.5, whereas the boy's total moment has become 516. So which one of this moment is bigger? Boy's moment, I can see. This is just to be a number. So this would mean,
Nothing, sir.
so this would essentially mean that whenever they are going to move away from each other by the same equal distance, both of them will increase the individual moment. As the girl moves away from the pivot point to the left, she's going to increase the anti-clockwise moment. As the boy moves away from the pivot, she's going to increase the clockwise moment. That is definitely a true thing. But are they going to increase their moment by equal measure? That answer is a no. And the reason I'm showing you this calculation is to convince you of this fact that which one is going to be bigger and which one is going to be smaller compared to each other. And you can essentially attempt this whole calculation for any other value, any other positive value on this case, and you'll always say that no matter what you use, very small or very big, you'll always end up the clockwise moment to become slightly larger compared to the anti-clockwise moment. And this is actually going to happen over here. If you wonder why is this happening like this, the reason is pretty simple. The reason is that for the equilibrium to exist, these two things needs to exist in this ratio. Whenever we increase both of these values by the same amount, let's say if we convert this into, let's say, if we add, let's say, 5 to both of them, we're going to get 48 by 60. If we increase this ratio by this one, you'll see that the total value of this ratio is now larger. Being the value larger means that the denominator got increased by a smaller fraction compared to the numerator. Does it make sense anyhow? আচ্ছা, disregard that. এটা actually তোমাদের এটা fraction দিয়ে তোমরা I cannot even explain this properly. I have it in my head, but I think this one makes better sense. We just would give it a little bit of trial, or you can actually show some trial calculation for to convince the examiner as well that let the boy and girl both move 0.1 meter away from each other. In that case, the new anti-clockwise moment is 478.15 newton meter, and new clockwise moment is 460 newton meter. So we can very well see that the clockwise moment will be larger. So the seesaw is going to tip down on the boy's side. Tip down means it's gonna go down on the boy's side. So that's the calculation variation that I can see over here. So if I'm about to write this answer, how am I gonna write this thing? They have said describe and explain what happens. The first thing I'm gonna write is okay. So I'm gonna write it this way. When both the boy and the girl slide equal distances along the seesaw from each other, both anti-clockwise movement from the girl and clockwise movement. I mean, I might not as well write the first part. When part I would not write. That's just quoting the question. Forget about that. So I'm gonna start with this way. After they move, that's it. After they move, comma, both anti-clockwise movement from the girl, I will look at the figure, and clockwise movement from the boy increases. But the clockwise movement from the boy becomes larger compared to the anti-clockwise movement available from the girl. So am I making a mistake here?
Sir, when I increase that distance between them to 1, then the girl like got more moment in her side in the anti-clockwise direction.
Right, really?
Yes, sir.
আমি কি এই ক্যালকুলেশনটা ভুল করছি কোথাও? Yes.
Sir, to get
Yes, sir.
478.5, you have to add 0.01.
Exactly. এই জন্য আমার কাছে ক্যালকুলেশনটা অফ লাগতেছিল। This was supposed to be 0.96, right?
ওই জন্য বুঝলাম স্যার, কারণ হলো গিয়ে মেয়েটার ওয়েট তো বেশি, ওয়েট বেশি হওয়ার কারণে তো
Exactly. এটা হওয়ার কথা না। I'm really sorry about this. I miscalculated. I'm so sorry. This is supposed to be 520 and this is supposed to be 516. So the girl will actually produce a much bigger moment, anti-clockwise moment, and the boy will produce a smaller clockwise moment. Both of their moment will increase. You should definitely mention that whenever they move away from each other, both of their moment, their individually produced moment, anti-clockwise moment from the girl and clockwise moment from the boy should increase. But the increase of clockwise moment from the brother is smaller compared to the increase of the anti-clockwise moment from the girl, which means ultimately the left side / the girl side will tip downwards and the brother side will go up. So that's how I would write my explanation. In my explanation, I would not essentially show some calculation, but I would definitely do this calculation anywhere else as a rough working, just to convince me of the fact, so that I could take a final decision for this. I'm really sorry, kids, for the misdirection of the miscalculation. Really sorry about this. So let's have a look at the examiner's mark scheme and see what the mark scheme have to give us for the solution for this question. So this is question number 11 from the moment chapter. So might as well have a look. That's 9. What are those? RMS. Have a look. This is I'm asking. You also have it with you. So it says both moments increase. That's 1 mark. Girls' moment increase more, or you can say girls' moment is now bigger than brothers, or you can say anti-clockwise moment is greater. Any of these 3 statements works to score you the A mark, and then seesaw tips down on girls' side, which means it goes down on this part. Have a look at the examination paper. Only the more able candidates produce logical and sequenced arguments to describe and explain what happened as the boy and the girl moved away from each other. Many candidates picked up one of the 3 marks available by stating that the seesaw tips down on the girl's side. Far fewer candidates went on to explain correctly why this should happen. Most candidates ignored the instruction given in the stem of the question, which was to describe and explain. So this is the important bit that you have to, in this case, you are asked to do describe and explain, which means you have to state elaborately what's going to happen. That's the describe part. And you have to also give a physics-based reason that what is the underlying principle or cause and why that's going to happen. That's the explain part. This question demanded for both of them. So this is the important bit. Explanation of বুঝা গেছে কি সবার? Everyone? আমি যে একটু ভুল করছিলাম প্রথমে ক্যালকুলেশনের জন্য, এই ভুলটা অ্যাকচুয়ালি করা ঠিক হয় নাই, না করলে ভালো হতো. That's why I was getting off as I was trying to decide, because in my brain this is not supposed to happen, like why is this happening, but then my calculation says it was happening and I had to recheck my calculation that I actually messed up. In my calculator, this is what I did, because I increased it by 0.8, 0.01, this was up to 0.96. In my calculator I typed 0.87, so that's the mistake that I did. So honest mistake. Sorry about that. বুঝে গেছে সবার? Sequencing of writing টা? I guess so. This pretty much concludes this AIMS paper 2 question paper. You can have more question from the other years' question. I can actually look it up and give you a list of the moment-based question from after October number 13. With these worksheets were compiled, I think I was up to October number 13. I think, yes, October number 13 was the last year that we have here. So a lot of questions have been published after beyond that session. So you can look up some additional interesting problem as well. So can I start the work energy part chapter right now, or do you have any other question regarding any of the MCQ paper or any of the other paper 2 question or any of the year question that you might have attempted for your school purposes, or you might have come across from your school and would like to have some discussion about that question? Anything that you want to throw at me regarding moment and stability chapter? Kids. You want to throw me nothing but silence? আচ্ছা, তোমাদের মধ্যে কে যেন আমার কাছে ওয়েবজের ওয়ার্কশিটের কথা বলছিল স্কুলে করাচ্ছে, সেই জন্য তোমাদের কার স্কুলে মানে তোমাদের কার স্কুলে ওয়েব করাচ্ছে এখন?
স্যার মাস্টারমাইন্ড।
স্যার মাস্টারমাইন্ড।
কতটুকু করাইছে?
স্যার থার্মাল শেষ করে এখন ওয়েভ শুরু করেছে, আর ওয়েভসে আজকে রিফ্র্যাকশন অফ ওয়াটার ওয়েভস পর্যন্ত শেষ করলো।
তোমাদের হাফ ইয়ারলি কখন?
ডিসেম্বরের দিকে।
Okay. I actually finished compiling the class notes for web chapter today. I have so I can actually start making the booklet for that one. Prior to the COVID, I didn't make booklets of this shape, so my notes are all haphazard everywhere. If you kids want/need some additional help classes for your school syllabus, we could arrange it for you. Or another thing that you can always do, if you want to have a better understanding for how to approach these chapters, This is something that I really recommend because that's what the having the YouTube lectures is all about. You can go to the playlist of the CIE O-level physics, which is just from your senior batch, and you can look up in here for the WEP chapter. So this actually started from electromagnetic class 3 because we had 2 other classes for which I did not upload because I don't have the voice for those classes. So this is particularly where it starts. And I have no idea how did this thing got added to my channel. Achha, never mind, I'll remove it. So here we have the electromagnetism, then we have some heat transfer, then here comes the waves chapter. So we have the same left lecture over here once again, connected twice. So let's remove that. So if you just go through here, you might as well come across the type of question that you might need help about. For example, over here we have the light chapters. So, and then I actually fell asleep in the class in this part, so I have a bit of a sleep rhythm. And yeah, these are the voice lectures that you can go through if you need some help. And I can actually start making the compilation printout for all of you, and have it delivered to you before your half-yearly exam, so that you could do some actual practice to go ahead. That's possible. That's just what I'm saying. Okay, I'll go for the discussion for the next chapter, which is work energy power in my head. So yeah, work energy power is actually pretty dumb. The reason I'm calling it dumb because there's only 2 formulae. Actually, a bit more than 2, but uh, two is pretty good. No, it's actually more than 2. And then there is just a bunch of theoretical understanding type of discussions. So if I just pull up the notes, I think it's somewhere over here. So let's go ahead and see what is in the work energy power chapter. Oh, by the way, আমি এই বুকটা শেষ করার পর তোমাদের কিন্তু ক্লাস টেস্ট নেব. I'll be sending out paper and then you have to sit for some sort of class test. আচ্ছা ইয়া এখন মইনুদ্দিন তুমি এখন এই বুকলেটটা পাও না, পাইছো?
স্যার আমি পেয়েছি তো স্যার।
আচ্ছা, কে যেন পায় নাই, আমার সাথে কথা হচ্ছিল মেসেঞ্জারে।
স্যার আমি বলেছিলাম।
তুমি এই বুকলেটটা এখনো পাওই নাই?
না স্যার।
স্যার আমিও স্যার।
আচ্ছা শোনো, irrespective of whether you have your roll number or not, if you are still doing the classes with us, send someone to our coaching tomorrow, or I mean after 11 a.m. 11 a.m. to 4 p.m. is the optimum time because in the duration both of
Sir,
our
11 a.m.
through 4 p.m. During this duration, both of our assistants are at coaching, and they are usually doing some office works being in the coaching. Usually after 4 p.m., at least one of them go out to do delivery, to make couriers to the regional spaces and also the courier office. So send someone and they just must have your name, and this is CIE physics for professor, that one. If you don't have your roll number, you just give them roll number, sir দেয় নাই বা roll number থাকলে স্যার roll number লিখে দিবা, and just write that you need the first booklet. So class 9 booklet আমাদের print করা আছে, you just need someone to pick it up from here. For those of you who do not know our address is very simple. It's 5 by 8 block D La Matia. I might as well give it to you right now. So I'm gonna resume I have resumed the recording. So jara booklet পাও নাই, send someone, or you can also show up by yourself to pick up the booklet. আচ্ছা, কোথায় গেল? So the work energy power over here, have a look at the definitions. Work is defined as a product of the force and distance with the direction of the force, which is pretty straightforward. So work is given by force into distance along that direction. If the force is horizontal but the distance covered is with a bit of an angle, then we use the cosine ratio to measure the distance between them. The reason we use the cosine ratio because if we try to draw a right angle triangle in this place, the horizontal distance covered or the distance covered along the direction of the force would be the cos part of this triangle. So let me just elaborate this figure a little bit so that you can convince yourself about the cos theta ratio a little bit better maybe. So have a look. This is a figure over here. So if I just label the stuffs to go through, this is the force that we're applying. Okay, let me use red, very easier to see. This is the force that we're applying, and to calculate the work done, we want to find out how much did the object move along this direction or along this alignment. So if the object in this case is definitely going somewhere, has to be a little bit up, and it's also moving a little bit to the right. So this force is responsible practically to do both of them, to give the object a little bit of height gain, to make the object to move along the distance. But the mathematical definition is that work done on an object is always the force in distance covered in the direction of the force, which means we have to find out exactly how far the object moved in the horizontal direction by distance. So we are trying to find out how much is this. This is our aim. This force multiplied by this horizontal distance will give us the total work done. So now if we have a look that this is, if I now just try to draw, join this distance right over here, maybe with a dotted line, you should be very clearly seeing a right angle triangle where this is the right angle. This distance is d, so I might as well label that. And because this is theta, the inclination of the surface is theta. This angle over here, because they are similar angles, corresponding angles, should be also theta. So have a look at, if you look at this right angle triangle, so let me label this a bit better. So this is the right angle triangle. Here we have the hypotenuse, here we have the adjacent. So I showed you in the earlier case, in the case for the scenario for breaking down of vectors or breaking down in components, that the adjacent components are given by cosine ratio and the opposite components are given by sine ratio, which means this length in terms of the hypotenuse will be d cos theta, and this ratio on this side will always be d sine theta. So for this problem, to calculate the work done by the force on the object, we are going to need this one. So that's why this part comes from. So yeah. So this is the part for the work energy power part for. And then it says the unit is joule, which is scalar quantity. 1 joule is given by 1 meter. The definition is pretty simple. 1 joule is the amount of work done by pushing an object by 1 Newton force and making 1 meter distance move in the direction of the force. So that just means that 1 Newton into 1 meter. So if we apply 1 Newton force on an object, and by applying that force, you can, if we move the object by exactly 1 meter distance in the direction of the force, in the direction of the force, student অনেক commonly লিখতে ভুলে যায়. They just write that if the object is moved by 1 meter, only write this much. But it's imperative that you don't forget this. To define the unit of force 1 joule, or to even define the quantity of work itself, you have to mention that the displacement is gonna be measured or have to happen along the direction of the force, which is very, very, very important. Students in many cases absolutely forget to mention this. So in this case, so the next part that we have, in almost every case of motion, friction is present. So when any object is pushed by a force, it must overcome friction force to move. So work done by the pusher is not equal to the net work done on the object. Now this is a very interesting part. In almost every case of motion, friction is present. Well, you can always have it, unless you are having an object that is falling through vacuum, you have friction. Either you have friction of contact friction, if it's a solid object, or you might have a rolling friction if it's a rolling object like a wheel or a solid cylinder of metal rolling up. If it's a rolling object, you're going to have rolling friction. Or if there is none of this, you can if you are moving simply through air, the air resistance is also actually a sort of fluid friction, which I have learned in our earlier chapters. So whenever any object is pushed by a force, it must overcome the frictional force to move. So if we want to achieve movement, first of all, we have to overcome the frictional force, and only then can we have the object actually moving. So work done by the pusher, or pusher in this case means the entity which is causing the object to move. It doesn't have to be a person. It could be an engine. It could be a rocket propulsion engine. It could be a spring. It could be anything. The pusher in this case means the entity or the authority which is trying to move the object by applying some force. That's what this word means. But the pusher is not equal to net work done on the object. So what do you mean by net work done? Net work done means the amount of work that is visibly seen, the amount of work that is actually achieved on the object. So in this case, the net work is given work done by the pusher minus the frictional loss. Now, frictional loss means that if, let's say, if I'm trying to push a block of wooden box, or block of, if I'm trying to push a box which is a heavy box which is on the ground, and if I'm trying to push it, first I have to overcome the friction, and then if I can apply force which is slightly bigger than the friction, then using that force I can start accelerating that object. So a significant portion of my work done would be continuously be wasted to overcome that friction. So how much frictional loss does happen in the process of moving an object can be also calculated by the exact similar formula of work done. Have a look. Here the work done was calculated by force into distance, and frictional force is also frictional loss, which is frictional work done, is also calculated by force into distance. But the reason it is loss, I mean, why is it loss if it has the same formula? Because friction always works in the opposite direction of the motion. So actual work done, force into distance, in this case, force into distance, both of these vector quantities, force and displacement, they should happen in the same direction, in the same alignment. So in this case, force is working from left to right on the object. The distance is also happening from left to right on the object. So they are parallel and in the same direction for it to be a positive work. Now, if one of them becomes reversed, for example, if you're thinking about the frictional force, if frictional force is working on the object, then that friction force would work in the opposite direction of the displacement. The direction in which the object is going to move, the friction force will always work in the opposite of that direction. That's why the total product will give a minus value, and that because of that minus value, we use the term loss. Loss means this is the amount of energy which will be by default be wasted within the movement process. So this is the idea for the frictional loss. We're going to need this equation quite a lot of times to solve multiple MCQ questions, and also a good number of paper 2 questions as well. This is a good question, that how can you calculate the frictional loss or frictional work done. Sometimes that is also the phrase that the examiners use to check the students' understanding. So that's the basic idea about work. We'll get more to this thing whenever we'll go further. So then comes the basic definition of energy. Ability to perform work is energy. That's just the qualitative definition for it, which is good enough for you. Unit is still joule. Work and energy are interconvertible. Interconvertible means what? That's given in the next sentence. Whenever work is done on an object, it gains energy, and vice versa. And vice versa means whenever any object has energy, it can do some work. So by doing work, we can give an object some energy, or if an object by default has some energy within itself, it is capable to perform some work. So that's why work and energy are interconvertible. And then we have types of energy sources. So here are some examples of the type of energy that we usually experience in our regular life. We have light energy, sound energy, heat, electrical, potential, kinetic, etc. All potential and kinetic energies are also called mechanical energy. Mechanical energy is a key term that we use in cases whenever we whenever what can I say? Mechanical energy definition আমি পরে বলতেছি I will go further down the discussion more, so there will be some examples discussed which may make it easier for you to understand. So this is the type of energy sources that we have, and then so in a name of energy, type of energy that we have, and then this heading is that we have two type of energy sources. So what are the authorities from which we can get energy? We can have two sources. One is the renewable source and one is the non-renewable source, and they are defined in a very specific set of words, not exactly similar to what their name proposes. So renewable energy sources means that it is that type of energy resource which is never going to run out, which will never run out. What does this mean? It means that this energy resource will keep on giving us energy for the foreseeable future, or at least for a significantly long duration of time, which we can consider to for the entire upcoming foreseeable future. For example, the sun. Sun has passed through about 1/3 of its useful life. It still has 2/3 of its useful life left, which is, I think, a couple of 100 billion years. So for our reasoning, a couple of 100 billion years of useful sun's energy made available to Earth can be considered to be a renewable source because it's not going to be finished. It's a free energy. It is always available to us. And then we have the non-renewable energy resources, which are the energy resources which will eventually run out. Now, one thing that I want all of you kids to understand very, very minutely and properly. So let's have a go through the read. Then I might start adding more to the discussion. Two energy resources are the non-renewable sources: fossil fuels and nuclear energy. Exclusively, these are the two energy resources which are non-renewable. Fossil fuels means coal, oil, gas. Fossil fuel can have only three versions in its solid, liquid, gas form, which is coal, oil, and gas. And nuclear energy. Nuclear energy is the basic process by which mass is converted into energy in the nuclear reaction, fission reaction, or chain reaction process. All other forms of all other forms are renewable, such as wind energy, wave energy, tidal energy, solar energy, hydroelectric energy, geothermal energy. So everything else, every other type of energy that you can think about are some sort of renewable energy resource. Now, here's one thing I need you to understand: that do not confuse energy sources with energy type. For example, if you say battery is a source of energy, battery is a energy resource. No, battery is not an energy resource. Battery stores chemical energy within itself, but the battery is not the thing that is created naturally from some source on its own. Battery is a human engineered manufactured product which can store some amount of energy that we can use at our requirement. A battery is a device to store energy. So battery stores chemical energy. That chemical energy was not created by the battery. That chemical energy was put into the battery by us human beings. Why did this chemical energy come into existence in the first place? For example, a battery has some sort of acid and some sort of metal cathodes and anodes, which actually does some reaction and give us the energy output. So you have chemical energy embedded within this part. And by allowing the reaction to occur in a controlled manner, you can liberate that chemical energy in the form of electrical energy. So battery is not an energy resource. Energy resources are the things or the naturally occurring stuffs from which we can make other form of energy. So battery is not a naturally occurring thing. It's an artificial occurring thing. You might wonder that, well, nuclear fission is also an artificial occurring thing. Then why is that is an energy resource? Because to make nuclear fission available, we have to have the nuclear fuel from the nature. Once we break it down into fission fragments and other stuffs by the chain reaction and so, we can liberate some energy out of it, which is actually not some. Nuclear energy is actually quite huge in terms of energy availability per mass of the fuel. But my point being that do not assume stuffs that is an energy source just because it has some energy stored within itself. Energy source means typically a naturally occurring source which can give us energy for some significant duration of time. Now, I'm going to talk about multiple other stuffs. So, but before I go into that, have to take a good look at this sentence. It says that all renewable sources are attributed to sun. All renewable sources are attributed to sun except geothermal. This is interesting. And if you wonder, how about the non-renewable sources? Well, fossil fuel, all the fossil fuel that we have available to us in today's world, they are also, we also got them from the sun, which got accumulated over millions of years. And we human beings have been burning it since the industrial revolution, so nearly about 200 years. And within 200 years, we have liberated about, I think, quite 500,000 worth of carbon that was trapped within these fossil fuels. So that's what we did. Now, uh, the reason fossil fuels are also came from the sun, because the whole idea of fossil fuel is that these are basically the remaining of old trees and animals which got buried underground and then got decomposed, and without the presence of oxygen, that decomposition products converted into some sort of petroleum or some sort of gas, and eventually those are the what we call the fossil fuel. So how did the fossil fuel get the energy in the first place? Well, the trees back in the day, they did photosynthesis. In that process of photosynthesis, they stored light energy, not heat, exclusively light. They stored light energy from the sun into chemical energy format. So either those trees died and that energy is now available in chemical energy. Either that happened, or those trees got eaten by the animals. The animals grew up, and eventually those animals died, and their body is now giving us the chemical energy. So if you wonder, the fossil fuel is also an energy that was made available to us from the sun, but it happened a lot earlier. And the reason we call it a non-renewable energy resource, because it is naturally irreversible. The word naturally irreversible means that uh, if you think for a very simple renewable energy resource, for example, let's say the wind energy. I'm not using the solar energy first, because wind energy actually helps me a lot to give you the idea. If we set up wind turbines in the path of high wind flow in some location, we can actually convert the kinetic energy available in the wind to be converted into electrical energy. It's possible. Once we take up that energy from the wind, that wind is not becoming unusable because of the temperature variation of the uneven heating from the sun. That wind is gonna travel to the location that it was traveling to, only at a lower speed. It might be a bit late, but it's not gonna be lost. And eventually, in the cycle of the season, in the cycle of the day, that wind flow will once again redirect. So you can have this wind energy available as long as there is uneven heating from the sun on the Earth surface. Uh, so we're gonna have it anyway. Extracting energy out of the wind is not gonna make this wind unusable for the next day. You are going to have this energy available from the wind as long as you have the means to extract the energy from the wind. So it's pretty simple. However, fossil fuels don't work that way. Once you burn a piece of fossil fuel, in any natural process, it will not be converted automatically for it to be available, those same molecules to be available for you the next day. It's not going to work that way. These were done by extremely compression, high pressure and high temperature chemical reactions, which gave us those fossil fuel fossil fuel stuffs. And once we burn these up, we're going to liberate H2 and CO2 in the atmosphere, and they're going to remain in that format for millions of years to come, unless they are once again photosynthesized into some other chemical form, but by the plants mostly. So this is why the fossil fuels are considered non-renewable, because they, once used, they will not be naturally replenished, which means if we keep on using them, there will come a point when this resource is going to be finished. Because no matter how big of a thing is, if it's finite, and if we keep using it, there will come a point when it will be finished. So this is why we are defining the fossil fuel as a finite resource. Although nuclear energy is actually a very concentrated form of energy. Actually, let me tell you the idea for what do I mean by this term, the concentrated form of energy. For any energy resource to be viable, not essentially viable, to be one of the measures or metrics for how much of an energy resource is actually lucrative to us is its energy concentration. Energy concentration means that to how many kgs or how many grams of mass from how many joules of energy do we get from unit mass of that fuel or unit mass of that source. Maybe the bigger it is, more excited we are about that source. For example, if we burn methane, we are gonna get if we burn, let's say, 1 kg of methane, we're gonna get some amount of energy. But if we burn, let's say, 1 kg of petrol, are we gonna get the same amount of energy? If we burn, let's say, 1 kg of butane or propane, are we gonna get the same amount of energy? So these are all hydrocarbon names of different hydrocarbon, but 1 kg of all of these pure hydrocarbons or all of these pure fossil fuels, are they going to give us the exactly same amount of energy liberated whenever we burn them completely? That answer is a solid no. Different bonds breaking give us a different amount of energy. So on all of the hydrocarbon, methane gives us the most amount of energy output per mass. So this is one of the reason we prefer to use it for a lot of heating purpose and everything. However, if you consider for nuclear fuel, in the nuclear fuel, actually we break down a certain radioactive nucleus artificially by shooting it with some thermal neutrons, and that neutron gets absorbed within the nucleus. It then splits into 2 smaller pieces, so it's sort of like an explosion. And within the explosion process, a small fraction of mass of the original nucleus gets converted into energy. Now, this conversion of energy into mass, or vice versa, is also possible to convert mass into energy. Both of them are possible. In this case, we are covering mass into energy discussion. This is an exclusively subatomic happening. And it is a micro case happening, or it's a quantum case happening. This is not a regular thing. This is not an obtainable behavior in our regular life. In our regular life means in the Newtonian world. Newtonian world means for objects which are bigger than an atom. So for scenarios that we're going to discuss for most of our syllabus or most of our physics discussions, we're going to consider mass as a conserved quantity, and we're going to also consider energy is also a conserved quantity. Conserved quantity means that the amount of these two individual variables will remain same after a series of happening. So if you start with a total of, let's say, 12 kg of mass in an experiment, no matter what you do, eventually after all of your experiment, that 12 gram of mass will remain 12 gram of mass. This is most commonly applicable for chemical reactions. Let's say if you have, let's say, 12 kg of methane, which you burn with the required amount of oxygen, and if you add up the mass of the two reactants, you're going to get the same mass of CO2 plus H2O after the reaction is complete. You're not going to get a different amount. You're going to always have equal amount of masses no matter what you do. And energy can be related from the bonds. So in this case, no energy was actually energy. So for chemical reactions, energy is not released from mass conversion. It is released from the bond breaking and bond creating difference. The point I'm trying to make is that for most of our purposes, for bigger than atomic scenarios, we are going to provide or we're going to consider that mass and energy are conserved quantities. And for lower than those scenarios, mass and energy can be interconvertible. আচ্ছা, আরেকটা জিনিস যেটা আলাপ করতে আছে সেটা হচ্ছে all renewable sources are attributed to the sun. How does this work out? আচ্ছা, nuclear energy, why nuclear energy is considered to be non-renewable? ওই জিনিসটা বলতে চাচ্ছিলাম. The reason nuclear energy is considered non-renewable because each individual radioactive nucleus, for example, the most common nucleus that we break down into nuclear reactors are the uranium nuclei, uranium-235 isotope more precisely. Once we break down an uranium-235 nucleus to produce energy out of it, naturally those two fission fragments or daughter products, the things that we get out of this breakdown process, naturally they will not merge together to reproduce that uranium-235 nucleus, which means, let's say, if on Earth you have, let's assume, 1 million uranium-235 nuclei at this second of the day, if we keep on breaking them, there will be less than 1 million, and the more you break, the closer you'll be approaching towards having that number to become zero, which means this is a non-reversible process for natural reasons. So once you break down a reactive nucleus, it has broken down, it has given you energy, its energy, nuclear energy to us, and that's it. It's not going to automatically recombine to give us a fresh uranium-235 nucleus. That's not going to happen. Because it's not going to happen, which means the more we use the uranium fuel or any other radioactive fuel for our purposes, the less of it is going to be available to us within the earthly environment, which means it is not getting replenished over the duration, like wind energy, for example. So that's why nuclear energy is also considered to be non-renewable sources, because this source will also run out if we keep on using it. There will come a certain point when there will be no more fissionable material available to us anymore. So then we have this part. So this is the first formula that we have, gravitational potential energy. Do we have no discussion about the other energy resources over here? There should be. Just a second, pull up an minute. No. Okay, I'm gonna give you some additional printouts in PDF form, which is not included here, from the IGCSE book, which I personally find pretty interesting to read. I'm just gonna show this to you right now, so that eventually, whenever you'll read, downloading it from our messenger group, it will be easier for you to understand what I'm talking about. So, yeah. Might as well attach this with the thermal chapter. I should remember not to forget this. This is actually pretty good read, and you can have access to this. So here we have the energy sources and the electricity generation. We can see that we have coal, we are heating up some water, we are refilling the car, blah blah blah. These are the two different forms of gas, natural resources. And then here the reason I want you kids to actually go through this part, because this is a good idea, that why uh, I mean, what actually is happening in the energy scenario for our requirement. So this is the typical view for nuclear power. So for any power station which works with steam generation. So here are the steam pipes, and this is the turbines, which is the generator, which is along this path at this end. And here we have a difference, that renewable energy resources, what does that mean? And we have two examples. So we have a lot of different energy resources with appropriate figures and everything. So this makes it easier for you to understand that how does that whole thing work. So I'm gonna deliver this to you, and I'm gonna take feedback from you about this thing in the next class. So I'm not gonna go through discussing all of the parts right now. I want you guys to give it a read first and have some questions from here. Monidin, this is the EdXL IGCSE book, which I don't have the whole book in PDF format. I actually had the whole book in some other software version. Then I screenshotted all of these pages and merged them together. Okay. So yeah, I would like you guys to read about this, the whole thing, 12 pages. Just read this. Stuff that doesn't make sense, you want me to discuss, just unmark those parts. And marking PDF is pretty simple. If you use it from your phone, you can use any of that thing. If you or you can just highlight this part, for example. Let's say I cannot highlight this part, but what is this? It's not an image. Select. Oh, this whole thing is an image. I actually cannot do highlight over here. Yeah, because I screenshotted the whole thing. As I just mark somewhere that what do you want me to explain, or I believe if I don't want to highlight, I can actually underline stuff over here. If we have a PDF, you can actually mark stuff. For example, If you want something to be discussed in this paragraph, you might give a question mark beside this paragraph. So let's say exclamation mark, and then you save it with those marks, because you can always get the fresh copy from the messenger. It will be there forever, as long as the Facebook works or the messenger servers work. So mark the places where you want me to discuss something new for you that doesn't make sense. We'll pick it up from, we'll pick this discussion in the next class, inshallah. If I go for the later part, the gravitational potential energy, it says, how do you define gravitational potential energy? Energy stored in an object due to its position. Due to its position means it has to be above a certain level. Now, the idea for above and below is actually relative. I mean, how do you define above or below? The idea of above and below only works as long as we are under the effect of some sort of gravitational pull that we can understand. Both of these two words are important. We have to be under the effect of some sort of gravitational pull that we have to be able to understand as well. We might, if it so happens that we are not under the effect of any gravitational pull, for example, let's say we are floating through the void of the empty space in some spacecraft whatsoever. There is no significant massive stars or planets around us, so there is no significant gravitational pull on our body. So that's just a case where gravitational pull is simply unpresent. That's scenario one. The scenario two is consider the case for the satellites which go around the Earth in continuous circular orbits, or consider the ISS, International Space Station, where there are people, but they apparently float around being weightless. What is actually happening? They are going around the Earth, and they are not actually, this whole contraption of International Space Station, it is not actually getting away from the Earth, not also falling towards the Earth, which means it is practically stuck in a circular, nearly circular, sorry, it's my sister calling my mom through my account, my bad. So the ISS, in which a lot of astronauts work for scientific research and purposes, so it's going around the Earth in a near circular, actually an elliptical orbit, but it's not falling close to Earth, it's not getting away from Earth, which means somehow it is stuck to the Earth. That is very simple. It's an object that has mass. The Earth's gravitational field is pulling that thing towards the Earth. The way it is actually not pulling towards, is not falling towards the Earth, is because it is continuously going in circular orbit. So it is using the entire of the available weight to maintain the circular motion. So all of the force that is weight of that International Space Station, it is designed to be used as centripetal force. Because it continuously uses that thing for centripetal force, it means all of the available weight of the International Space Station or that satellite is being used as to maintain the circular motion. It does not have any force remaining for it to actually fall towards the Earth. Because I told you in the very first class, quite an early class, that once we use a certain amount of available force for one purpose, we cannot use it for a secondary purpose. We can only use a certain force for one purpose only. So in the way satellites work is that the weight every satellite has, because of the weight and attraction of the Earth, they use all of their weight to maintain the circular motion, to continuously go around in circles, to continuously change the direction of the velocity. And that's why they don't have any much force left within them to actually get closer to Earth or something like that. So that's in that case, or in that scenario, for people or astronauts who are actually inside the International Space Station, who are doing research works and stuffs, they are under the effect of gravity. Yes, they are under the effect of Earth's gravity, but they are moving in at such speed that they are not going to able to perceive that gravity, because they will be continuously using that amount of weight that they have. Do they have weight in this case? Yes. Do they sense it? No. Why don't they sense it? Because they are not going to exert that weight force onto any surface. They're continuously using their own weight along with the entire satellite to continuously go around in circles around the Earth. And because of that, they don't have any much force left to them, so they can exert that force onto anything. So if they are placed in a location in the in that sense at the satellite, they're gonna be staying there. The way we perceive our weight is by the reaction force on the surface that we stand or sit or lie down. If you're standing on the ground, your feet, I mean, is continuously experiencing, the bottom of your feet is continuously experiencing the upward push from the surface that you're standing on. That's the reaction force that we obtain in response of the weight that we exert on that surface. If you're sitting down, your hip and your thigh experiences that force. If you're lying down, your entire lower side of your body experiences that force, which means as long as we're in some gravitational field, some portion of our body is always experiencing an upward push from the surface on which we are on. Which means, or if we're not on any surface, if we are on with some harness, for example, if we're hanging with something from above, you'll also experience that downward force either in terms of the strap pressure, or if you're hanging by holding on a rope, you'll be experiencing that downward pull because of the friction force between your hands and that rope. So there's always physical means by which we can sense that something is pulling us down. The way we experience that something is pulling us down, because we experience an upward force from anything that we are attached to in our regular life. So that sensation of upward force / reaction force makes us understand that weight is working on us. If some person is unable to achieve that sensation of reaction force, they will feel like that weight is not there. That's what happens for an astronaut, because they do not have any force available to themselves, any part of their weight that they can apply on a certain surface continuously. That's not going to happen because they don't have that available. So they can apply a force onto a surface, and by Newton's third law, that surface is going to give them equal and opposite force. Practically, this is exactly how they move around within the International Space Station, because other than that, they cannot move around. So they have to hold stuffs and move around by holding stuffs like that. So why am I telling you all of these stuffs? Because the idea of gravitational potential energy is applicable whenever any object is above a certain level, and the word above is applicable when there is a perceivable effect of weight onto this object. So there have to be gravitational force, weight, and that weight has to be perceivable as well. So then the discussion comes, whenever we move an object in a gravitational field, if movement causes it to get further apart, for example, an object lifted above means its distance from Earth has increased, we have to do work against gravitational force, that is weight. This work is stored in the object as GP, gravitational potential energy. So whenever we are doing work against the weight, we are going to store energy within it. So if we lift up an object, the weight of the object is necessarily trying to pull it down. If we lift up an object, we have to apply at least equal amount of force as the weight of the object, and then only we can push it upwards. So in the process of working against the weight, we're going to store energy within the object. And if we allow the object to fall, then the weight of the object is going to pull it down, and in that case, the GP will be converted to other form, and in that case, GP will decrease. So if we work against the weight, GP increases, which is lifting up. If the weight itself causes the object to move, which means it's falling down from a given height, in that case, GP converts to some other form. So that's GP decreases and other form of energy increases. Here is a very simple figure for the GP calculation for an object. We have an object of mass m. If we lift it up by a height of h, then the total G work done will be given by force into distance, which is work into height, which is mgh. In GP calculation, it's very important to understand আচ্ছা এটা where হবে পোলাপান, এটা একটু কাট করে নাও. I think it's definitely my mistake. This kid is actually a really good student. I believe my handwriting was so poor that they read it as when. পোলাপান এটা একটু তোমাদের নোটসে কারেকশন করো. In GP calculation, it's very important to understand from where height is measured. করছো? হ্যালো,
জি স্যার করেছি।
ঠিক আছে. In GP calculation, it is very important to understand from where height is measured. If we hold a book at some height above a table in the second floor, then the book has different GP from different levels.
What are those different levels that I'm talking about? So think about it. If on the second floor of a building, if you're holding a book above a table, it's gonna have different GP corresponding different levels underneath that. For example, if those one level given the table surface. So book to table surface, with respect to the table surface, will have some GP. Floor of the second floor. If you don't consider table surface for your ground level, h equals to 0. If you consider the floor of the second floor as your reference height, then with respect to that height, you're gonna have some GP. Then you can have floor of the first floor, for the ground floor. So necessarily bigger H gives more GP, more MGH and more GP. So it is important from the question that you understand it very precisely, that for that question, what is our ground level or what is our H equals to 0 level? H equals to 0 level কথাটা মানে হচ্ছে যেখান থেকে আমরা height measure করা শুরু করব. So if the object is located at H equals to 0 level, that object does not have any GP. Simple. As the object is pulled above H equals to 0 level, it starts to gain GP, and the higher we pull it, the more GP it will have. So if an object is somehow already at a higher height compared to our regular experience, then how much GP does it have? To be able to express that quantity, we have to first determine with respect to which surface. For different surfaces of different heights, the stored GP amount can essentially be different. So we have to understand this aspect from the question very, very clearly if maths are to be correct. Here we have a little bit of derivation for the formula for kinetic energy. Kinetic energy of an object is given by half mv square. Half is a mathematical constant, and then m is the mass of the object. V is the speed of the object at that instant for which we are measuring the kinetic energy. In the lower part of this figure, we have a little bit of mathematical derivation for how this formula come into existence. I mean, it's a derivation of k equals to half mv square, but it's not important that you have to know this derivation because it's not included in your syllabus as far as I know. I believe so. I'll still look into the syllabus, but I just gave this proof to the kids so that they can understand that where did this half come from. When the kids ask me that, sir, where did this half come from? Mv square, okay, fine. So this is just the mathematical definition. So what is happening over here? We are assuming that this object over here was stationary, and we applied a force F on the object as long as the object was moving over the distance of S. So object is moving over the distance of S, and we are keeping we have maintained the applied force F onto the object. So it's not that we have just pushed the object by F force and then the object is moving on its own. No, we are keeping on applying the F force over the duration of F, over the duration of S. So in that case, the total work done of the object will be force into distance covered, that is F into S. Force into distance covered in the duration of the force. You see, I'm also forgetting to mention that. So it has to be mentioned. So work done on the object is given by F into S. So K of the object should be exactly same. So we can write it as MAS. Now we're gonna somehow try to deal with the variables over here for replacement. We know V square equals to U square plus twice S. If you wonder why are we choosing this formula, because on the right side of the K of the object of equation 1, you see that it gives F into S, which gives us MAS. So we would like to have it replaced with some property of the object. So AS, replacing the AS part would be easier. That's essentially what we're trying to achieve here. So that's why we have gone for the V square equals to U square plus twice AS, because within this formula, we have the AS part as a product. So because the object started from rest, that's why we are replacing the U as 0. So it is becoming V square equals to 0 square plus twice AS, and equals to AS equals to half V square. If we replace that AS value into the equation, we get Fs K of the object equals to M into half V square, which gives us the half M V square expression. So that's that. So kinetic energy is the second formula that we can see from this chapter. The third formula should be power. Okay, I just talked about this a little bit earlier. Oh no, we do have the law of conservation of energy before showing up power. Law of conservation of energy is actually very simple. I'll pick up the lecture from this point in our next class. I'll upload the PDF for that book in your channel right now. I want all of you kids to go through that. If you have any question, you ask me questions about this in the next class. Thank you very much.
Assalamu alaikum, sir.
Assalamu alaikum, sir.
Or if any of you have come across any of the problems, for example, let me just be very clear and frank to you about this. আমরা motion chapter ta pura porsi. We also discussed the solution for the paper 2 as well. We studied the elasticity chapter. We also studied the artisan ki chapter chilo majkhane elasticity chhara moment which this is the moment chapter. So if you come across some question regarding this chapter's involvement that your school teachers they made you attempt, or you came across this problem through some class test or something like that, or maybe you tried some problem from the recent years which questions are not included in the worksheet, and you do have some problems about any of those questions that you would like me to take a discussion in the class, do feel free to share those questions. I am all ears, and questions that I haven't made you to practice within the worksheet, I'm very much willing to discuss problems of those questions. So it really does not matter, kids. Remember these words very carefully. It really doesn't matter from which source do you pick up this problem. Even if you're doing another physics coaching elsewhere and you got some problems from that teacher's class test which you would like me to discuss, bring that up in the class. No big deal. There's no prejudice over here, and there's no confusion over here. I'm gonna be I'll try to help you for all physics related problem that is applicable for your level of O-levels level of understanding. So no holding back. Do I make sense?
Yes, sir.
Yes. So if you have relevant questions, feel free to share them in the class. Thank you very much. Allah Hafiz.